In this next sequence of videos, we're going to take a look at transformations from R2 to itself and from R3 to itself, sort of um, the basic transformations here. We're going to start this video with reflections. So we'll start in R2 and then we'll go to R3. Now, the textbook here, this is just a table copied out of the textbook. They focus on the simplest reflections, and we will look at all the reflections here. In particular here, they have this first one, which is this reflection across the x-axis. So any point xy, think of the x-axis as a mirror, would be reflected down to the point x minus y. The x-coordinates stay the same, and the y-coordinate switches sign. Right? The one down here would be transformed up to there. Now, when we're making the matrix for each one of these transformations, there's a couple different ways of doing it. One is I see this where the first, the first component here is x, and the second component is minus y. So whatever matrix I create, when I multiply by xy, right, that I need to end up with an x. Well, when you in the first component, I mean to get an x. So it's going to be x times 1 and 0 times y. Right? So the coefficients I see in front of x and y here are 1 and 0. Likewise, the coefficients I see here are 0 and minus 1. Right? There's a 0 in front of the x and there's a minus 1 in front of the y. So that's one way to think about how to get this matrix. The other way is to think about what happens to each of the basis elements. Where does the vector 1, 0 go? So if this is the vector here, 1, 0, when you reflect it across the x-axis, it goes to itself. It doesn't move. So where does 1, 0 goes to? It goes to 1, 0. Where does 0, 1 go to? Well, when you reflect that across the y-axis, it'll end up down here. Right? So it goes to 0, minus 1, and that's the second column. And mainly that's the way I think about how to come up with these matrices. Look at where first basis element goes, E1. Look where the second basis element goes, E2. And those are the two columns. Okay. Reflection across the y-axis would take this point xy and reflect it this way. So it goes to minus xy. In this case, the 0, 1, no, this would be 1, 0, gets reflected to minus 1, 0. And 0, 1 doesn't move. So it's still 0, 1. The other of the simple reflections here is across the line y equals x, and this essentially just interchanges the roles of x and y. The point xy turns into the point yx. Right? So in particular, the point 1, 0 goes to 0, 1, and 0, 1 goes to 1, 0. So there's the first basis element going to 0, 1, and the second basis element going to 1, 0. Now, what about reflection across any other line? Well, let's do this. So here is an arbitrary line through the origin. Now I have to have it through the origin because one of the things I know about all these transformations is that the 0 vector has to go to the 0 vector. So I can't be reflecting across some line up here because then 0 would be sent somewhere else. The origin has to be on the mirror for this things to work here. So anyway, I'm going to describe this two different ways. One is by saying, what's this angle? Right? Let's call that angle theta. And I will come up with a matrix that describes reflection across this in terms of theta, and then I want to come back and say, how about if I describe this as y equals m times x? Because I might have it written that way, so I want to come up with a matrix that describes the transformation in terms of m. Okay. So the thing I'm going to do is I'm going to look at where does 1, 0 go to, and where does 0, 1 go to. Well, the thing about reflections is it doesn't change distances. Essentially, when you reflect perpendicularly across. So I'm going to go to there and then go the same distance across onto the other side. So I get to there. And in particular, when I connect this to the origin, this angle right here should be the mirror image of that one, so that should also be theta. So what I see here is that this point right here is at an angle of 2 theta, and because this had length 1 getting out to here, this also has length 1. So to come up with the xy coordinates, all I need to do is drop a perpendicular and do a little trig here, because I've got an angle of 2 theta, and a hypotenuse of 1, so I know that the coordinates here are the cosine of 2 theta, sine of 2 theta. So the first column of my matrix is cos 2 theta, sine 2 theta. Now, the next thing I got to figure out is where does 0, 1 go? Well, it's going to be the same thing where you drop a perpendicular down here, and then you keep going the same amount on the other side, and it'll end up down here somewhere. What I need to do is I need to figure out what this angle is right here so that I can use cosine and sine of that angle, again, because I know the hypotenuse is 1, because that distance from here up to there was 1. So what is this angle? Well, this angle right here is pi over 2 minus theta. And the angle down, so if I go up to theta and then back that same amount there, so this would be theta minus pi over 2 minus theta. And so this is 2 pi, no it isn't, it's 2 theta, because there's a theta and a minus minus theta, and then minus pi over 2. So I'm not going to write this column over here yet, but I do know that the coordinates of this point now are the cosine of 2 theta minus pi over 2, comma, the sine of 2 theta minus pi over 2. And I could just write those as my column here, but it turns out that these simplify because pi over 2 is a nice angle. Right? Using an identity here, cosine of a difference, this is the cosine of 2 theta cosine of pi over 2 plus the sine of 2 theta sine of pi over 2. And the cosine of pi over 2 is 0. Sine of pi over 2 is 1. So this just turns into a sine of 2 theta right here. And for the sine of 2 theta minus pi over 2, I'll use another identity. This would be sine of 2 theta cosine pi over 2 minus cosine 2 theta sine of pi over 2. And again, this one is 0, this one is 1, and I just end up with minus the cosine of 2 theta. And there is my matrix in terms of this angle. Okay. Now, what if I wanted it in terms of m? The thing I can do with m is the slope is rise over run, right? It's the rise over the run. Well, that's the tangent of the angle, right? Let's do a little work over here. I know that the tangent of theta is m, which means if I draw this picture here, if this is theta, and I call this m, and this 1, then the tangent of theta is m over 1, and I can use the Pythagoras to get the hypotenuse of 1 plus 1 squared plus m squared, take the square root. What this allows me to do is to change sine and cosine of theta into algebraic expressions of m. So for instance, so the cosine of 2 theta is cos squared theta minus the sine squared theta, which in terms of m here, the cos of theta is 1 over this, so if I square it, it's 1 over 1 plus m squared. And the sine of theta is m over that thing, so if I square it, it's m squared over 1 plus m squared. And when I add those two fractions or subtract those two fractions, I get a 1 minus m squared over 1 plus m squared. Likewise, to do the sine of 2 theta, well, that's 2 sine theta cos theta. All kinds of trig coming in here. We like trig. So this is 2 times the sine of theta, m over the square root of 1 plus m squared, times the cosine of theta, which is 1 over the square root of 1 plus m squared, for a grand total of 2m over 1 plus m squared. And so I can rewrite this thing now. The cosine of 2 theta is 1 minus m squared over 1 plus m squared. The sine of 2 theta is 2m over 1 plus m squared. And the sine of 2 theta again is 2m over 1 plus m squared. And minus 2 theta would be, multiply this one by negative 1, it would be m squared minus 1 over 1 plus m squared. And so both of these represent matrices that would reflect any point. You give me an xy, I will multiply that xy by one of these matrices, xy, and it will tell me the resulting point over there. This one in terms of the angle, this one in terms of the slope of the line. Okay. Now very quickly, let's take a look at R3. And the three basic reflections are reflect across the xy plane, reflect across the xz plane, and the yz plane. Right? If you're reflecting across the xy plane, the z-coordinate goes from positive to negative or negative to positive, switches signs. X and y coordinates stay the same. So there we go. X and y are staying the same, and z is switching. I see that again as if I multiplied by x, y, z. The first thing I would get would be the x, the second thing I would get is y, and the last one is negative z. On the other hand, I also see it as, E1 doesn't move when you reflect across the xy plane because it's in the xy plane. E2 doesn't move when you reflect across the xy plane because it's in the xy plane. And E3, well, E3 does move when you reflect. It goes down below. It goes to 0, 0, minus 1. Likewise, reflect across the xz plane. It's the y that turns negative. So there's a minus 1 there. Reflect across the yz plane. It's the x that turns negative. So there's a minus 1 there. Now, we could also reflect across any plane, and it looks like I'm ready to do that. I'm going to do that right here. What I have is I've got a plane in space here, and this is the normal vector, ABC. So that's perpendicular to this plane. Then I've got some other point, which is x, y, z, and I want to figure out where is it going to. Well, first of all, it's kind of hard to see where it is, but let me drop a perpendicular down to the plane. Let's say it's right here, is where that perpendicular hits. And then when you reflect across the plane, I have to go the same amount down here, okay, to this point down there. So this vector gets reflected down to this one. Now in this picture, although it's not immediately obvious and I haven't said so yet, but I'm thinking of this as the origin right there, that your coordinate system goes right through that spot right there. That's the origin. So this one, I think, rather than trying to figure out where each of the x0, y0, where E1, E2, and E3 go, I'm just going to figure out where x, y, z goes. I can actually do that by using projections, because what I really would like to do is I'd like to take this vector right here that I'm starting with and add on 2 times this vector. But this vector headed downhill here is the same as the projection onto, well, it's the backwards, it's the negative of the projection of this vector onto the normal vector. So this vector here is in the direction of the normal vector. This, being perpendicular to the plane, is parallel to that thing. And so I just need to project x, y, z onto n. Well, I know how to do that. The projection of x, y, z, so the projection onto n of the vector x, y, z is, you take the dot product of the two of them, so that's ax plus by plus cz over the dot product of n with itself, so that's just a squared plus b squared plus c squared, and then multiply that by n. And so the point that I want down here is the original xyz, xyz minus 2 times this projection. Now that I have that formula, what I'm going to do is I'm going to switch back to saying, where does 1, 0, 0 go? Where does 0, 1, 0 go? And where does 0, 0, 1 go? Because I think it's easier for me to just work with numbers. That if I plug in 1, 0, 0 for the x, y, and z, then what I can see is the x coordinate is going to be a 1 from this one. I've got a minus 2a here, and then that's multiplied by a. Sorry, I got a minus 2a over this square root of a squared plus not square root. Anyway, whatever this denominator is. So I think my x coordinate to start with there, let's start making the matrix. I've got a 1. I've got a minus 2a squared over a squared plus b squared plus c squared. For the second coordinate, there's a 0 here. This is still negative 2a, but now I'm multiplying it by the b. So I would have negative 2ab over a squared plus b squared plus c squared. And likewise, the third component is 0 minus 2a times c over that denominator. So it's minus 2ac over a squared plus b squared plus c squared. Now where does 0, 1, 0 go? So I'm plugging in a 0, 1, 0 there. So this is going to give me a negative 2b this time, or is it something else? No, it's not 2b. So I'd have so the first coordinate, this is a 0, and then I'd have a minus 2b times a. So I got a negative 2ab over a squared plus b squared plus c squared. And the second coordinate, I have a 1 minus negative 2b times b, so negative 2b squared, and that's over a squared plus b squared plus c squared. You've got to be careful the 1 isn't over that, just this is. And then the third one would be a 0 and a negative 2b times c, so negative 2bc over a squared plus b squared plus c squared. And the last column is 0, 0, 1, 0, 0, 1, plugging in there. So the first coordinate gets a 0 out of here and gets a negative, this is now a negative 2c times a. So this is a negative 2ac over a squared plus b squared plus c squared. And then this is a 0, and this is a negative 2c times b, so negative 2bc over a squared plus b squared plus c squared. And lastly, there's a 1 minus negative 2c times c, so negative 2c squared over a squared plus b squared plus c squared. Whew, that was non-trivial. Okay, and it's possible I could get a common denominator here and simplify this a little bit, but this matrix, although it looks kind of crazy, really isn't, it's not that hard to get. It's stuff that we've done this quarter. We know how to take a projection. Once we know that, we can just subtract this vector plus those two negative vectors going down, and we end up with this matrix here. So there you have it, reflections in R2 and R3.